So if you are looking at the related rates section on the website, you will notice that I thieved a problem set from someone, and I have given them credit as appropriate. So this is a sheet borrowed from the University of Utah, one presumes Dr. Peterson's sheet. So I'm going to do the first one for you so that you can get a feel for it. Unfortunately, the related rates and the optimization problems are something that you really just have to sit down and bang your head on the wall for a bit before you really wrap your brain around what you're doing, what it's asking, and then how to manage the pieces. So this is one of those topics like trig identities where I can't show you how to do it because every problem is different. You have to use a little bit of critical thinking in order to figure out which pieces you have, which pieces you need, which models you have to use, what things you have to shove from one model into another in order to make the model useful. And you can see how that gets to be quite a library of problems very quickly. So I'll do one for you, and you can give it a try and see how it goes. And then if there are tears and recriminations afterwards, then maybe we'll try another one. Okay, so I'm just going to pull up the first question there. Alright, so a conical paper cup 3 inches across the top and 4 inches deep is full of water. The cup springs a leak at the bottom and loses water at the rate of 2 cubic inches per minute. How fast is the water level dropping at the instant when the water is exactly 3 inches deep? Express the answer in inches per minute. Do you even know what an inch is? It's okay. Express the answer in inches per minute. Note the formula for the volume of a cone is base radius r and height h is pi third r squared. They even gave you the formula. Isn't that handy? So we're going to write that down because you probably need it. Volume of a cone is pi over 3 r squared h. Lovely. Now if you were to go through and you were to piece through the information that they've given you, which we're going to do right now, we're going to end up collecting a whole bunch of stuff here. If this were grade 9, you would be expecting to have a height and a radius given to you so that you could put the height in, the radius in, and calculate the volume. Or if you were feeling very advanced, you'd be handed a volume and a radius and asked for height, etc. You'd be using the static model, right? Like if the radius is this and the height is that, then the volume must be this. Right? That's what these equations have done for you in the past. If you caught it when I was reading it, the question isn't asking you what the height is. It's not asking you what the volume is. It's asking you about how the water level is dropping. So that's not a fixed number, right? That's not a feature of the cone. That's a feature of the height of the water dropping in the cone. So it's a change in time. So we're going to need a derivative by time here before we get too carried away. So just for fun, why don't we do that first? So if I took this v here and I use the implicit differentiation skills that you just picked up and I do dv by dt. So here we go. So that's the change in volume by the change in time. I have pi over 3 is just a constant. Now here I've got r squared times h. That's a product rule, so I'm going to have to do that. But you notice I'm going to be taking the derivative of r by t and h by t, and neither of those match, so I'm going to have those correction factors built into my derivative when I'm done. So here we go. Derivative of r squared is 2r, but r is not t, so I need a dr dt. Multiplied by the h, because I left that alone, plus the r squared, because I leave the first one alone. The derivative of h would be 1, but h is not t, so I need dh by dt. And a closed bracket. All right, so if you look at what you've got there, I have how the volume is changing over time. So that'll be something in cubic inches per second or cubic inches per minute. The radius, so that's the inches of the radius of the cone. I have dr dt, that's the change in the radius over time. So the radius of the cone is either growing at a certain rate or shrinking at a certain rate, and that should be in inches per minute or inches per second. I have h, which is the fixed height of the cone at a particular moment in time. I have r, which is the radius at a particular moment in time, and then I have dh dt, which is the change in the height over the time. Now that's a big mess, but if you think about a cone full of water, right, like cones like this, and it's got a round top, if you let the water start dropping in that cone because the volume of the water is changing, the water will take the shape of the cone cup, but the cone of water, not the paper cone, the cone of water inside the paper cone is going to be shrinking as water leaves. The water cone is going to be getting shorter. The dh dt will be negative, right? It's shrinking. And the radius of the top of that cone, as the water drops, it has to shrink as well. Not the paper cone, the water cone that's inside of it, because that's the thing that has the volume change. So you have to let that roll around in your brain for a minute. I'm going to go back to the text, and we're going to start hunting for these, because many of these things are numbers. So we're just going to be able to drop them in and then work out whatever quantity it is we're trying to solve for. So I'm going to go back to the text, I'm going to read it to you, and I'm going to sort of pull out the information as I find it. So first sentence, a conical cup 3 inches across the top and 4 inches deep is full of water. Well, that's the paper cup. That's not the water cup, but I'm gonna write that down maybe over here. So it has a radius of 1.5. And it has a height of 4. Okay. Next sentence. The cup springs a leak at the bottom and loses water at the rate of 2 cubic inches per minute. 2 cubic inches per minute. That's a change in volume over time. So I'm going to record that up here, because that's probably important. Change in volume over time is -2. Negative because it's losing water, not gaining it. Next sentence, how fast is the water level dropping? It's doing this. How quickly is it dropping? So this is the height measurement. So it's asking for dh dt. All right. How fast is the water level dropping at the instant when the water is exactly 3 inches deep? So that's a height. Okay, so if you go through, and that's it, that's the end of the question. Express the answer in inches per minute. So I have this, which goes here. I am asked for this thing, and I've been handed a height of 3. And if you notice, that leaves the r not filled in yet. It leaves the dr dt not filled in yet, and it leaves this r not filled in yet. So we can't proceed until we know what r is, and until we know what dh dt is. And that's what this was for. This thing is trying to point out to you that the cone is a triangle that's been spun around in a circle. So any cone that fits inside this cone has to have the radius and the height locked in the same proportions. So here, the height of this cone compared to its radius is 4 compared to 1.5. Now that is gross, and you don't usually leave decimals in the bottom of fractions, so I'm going to fix that. Instead of 4 out of 1.5, I'm going to call this 8/3. So h over r equals 8/3. And what would be more useful is if I draw it in a place where you can read it. So let me try that again. And what would be even more useful than that is if instead of h divided by r equals 8/3, if I could write h as an equation. So I'm going to take this r, I'm just going to cross multiply it up to the other side. Like that. Okay, lovely. Would be even more useful than that, because if you look over here, I have h. So I'm going to put h into this equation and calculate what the radius would be. So I'm just going to do a little rearrangement here, so that r would be 3/8 of h. So the 3 comes up, 8 goes down, and I'm going to put it over here. Okay. So what's also super helpful is if I took this thing and I took the derivative by t, I'd find that dr by dt is 3/8 dh dt. So I have all the bits I need now in order to solve this particular problem. So I'm going to go back to this model here, and I'm going to fill in this, the 3/8 dh dt for dr dt, and I'm going to fill in 3/8 of h for r and for r squared. I'm going to erase this down here because I need some room. So dv dt is pi over 3 to this thing here, 3/8 of h, h plus r squared, I'm using this again, 3 squared is 9, 8 squared is 64, h squared is h squared, so this would be 9/64 h squared dh dt. And for those of you watching at home, some of you are probably screaming that I forgot this dr dt, and you're right. So I'm going to find dr dt here, and I'm going to put it in between my h and this plus sign. dr dt is 3/8 dh dt. And then this h was still here, plus that mess. Ugh. Okay, but I can keep shrinking this down because I have an h times an h there, so that's an h squared. So I've got dv dt equals pi over 3. 3/8 times 3/8 is 9/64 times 2 is 18/64. H times h is h squared with a dh dt plus 9/64 h squared dh dt. Alright, now this is h squared dh dt, this is h squared dh dt, there's 18/64 here and 9/64 here for a grand total of 27/64. and even better, 27 divided by 3 is 9. So I've been asked for dH dt, which is here, there. I've been given a value of h, which is 3, and I was given a dV dt, which is -2. So I just have to drop these things into this mess here and solve for dH dt. So dV dt is -2, 9 pi over 64. Height was 3 squared dH dt. So if I move all this stuff over, I'd end up with -2 times 64 divided by 9 pi divided by 9, because 3 squared is 9, equals dH dt. Okay, so the grand, you can't see that, the grand total there, 2 times 64 is 128, and 9 times 9 is 81. So if I were to sort of move this up here, we've got dH by dt is negative 128 over 81 pi. Gross. So what does that mean? It means that if you fill a cup with the dimensions that we were told in the first place, and you cut the bottom so that water starts to drip out of it at 2 cubic inches per, what was it, minute? Yes, 2 cubic inches per minute, then the height of the water in that cone is going to be dropping, which is good because we got a negative number here. The height of the water in the cone will be reduced by 128 divided by 81 pi, whatever that is, every second at that particular moment. Now, why is that in there? Well, because if it were full, the height is dropping less quickly because there's more water at the top of a cone. So the rate at which the height is changing depends on when you actually take your snapshot of this experiment. And you can see that in the math here, right? This whole relationship has a height in the equation. So you have to know specifically when you're asking so that you can get this number spit out. If you were super good at this, you wouldn't ask about a specific height. You would look at this, and then you'd sketch it so that you could get a picture of how the height was changing at all points in time. That's what's really useful, but it's a bit much to ask at first. So the first problems you're going to try are ones where they give you a geometry, and then you have to do your implicit differentiation over time to find all the rates of change and stuff. And then they're going to park in a few bits of information and ask you for one of these rates at a particular moment in time or space. That was a lot. We're going to do the same problem again, but I'm going to go a little faster, and I'm going to make these substitutions before I do the derivatives, so that maybe you can see that it's not quite so scary, because this was a touch intimidating. So I'm going to erase it, everything except for the cone, and then we're going to talk through some of this logic again. So let me find my trusty paper towel here. I'll just erase this and come up with it all again. Okay, so I have pi over 3 r squared h. Now, if you notice at the very top of the word problems, Dr. Peterson left you some hints for how to sort of proceed. So the first one was draw a diagram and label the quantities that don't change with their respective values and quantities. that do change with respect to time as variables. So he's asking you to draw the cone. So if we do that, here's your cone. And it has a radius of 1.5. And it has a height of 4. Okay, lovely. So what you've been handed there is the ratio of sides. So it doesn't matter how high the water is. If the radius is 1.5, then the height would be 4. If the height is 2, then the radius would have to also be half what it is. So we'd be down to, what is it, 0.75. So we're going to use that relationship to make a replacement in this before we do the derivatives. So what did I say there? If you compare the radius to the height, the radius is 1.5 and the height is 4. And that's a fraction faux pas. You don't do that. You would write that as 3/8. So radius is 3/8 of height. Okay. So the next thing that the sheet prompts you to do is mathematically specify the rate of change that you were looking for and record all other given information. Well, we're working on that. The very bottom of this question said, express how fast is the water level dropping? So we know that we're after dH dt. So that's what I want. So I'm going to look at this thing, and anything that's not an H, I'm going to get rid of it. So this pesky R here, if you remember, it generated the product rule. It made everything a mess. So I'm going to use this fact about R to get rid of it in this equation. So if I do that, 3/8 of H squared H. So I just replaced the R with the 3/8 H that we have here. 3/8 squared is 9/64. H squared times H would be H cubed. So there we go. I'm going to take the derivative now. So dv dt, that's a constant. This is a constant. The derivative of H cubed is 3H squared, and H is not T, so I need that correction factor, dH dt. I don't know about you, but that was a lot easier. It's also really handy that this 3 here divides out that 3. So if we go back to the question, it says find an equation involving the variables whose rates of change you were looking for and that you have been given. Ooh, we already have that. Number 4, implicitly differentiate the equation found in step 3 with respect to time. Ooh, we did that too. Number 5, state the final answer in a coherent form, being sure to specify the units of the answer and being sure so we have to do some numbers here. So I was asked for dH dt, which I have an expression for here. I need an H and I need a dV dt. And if you recall from what we were doing before, in the text it said that dV dt, it was losing 2 cubic inches per minute, and it wanted to know when the height was 3. So I'm going to put those numbers in here. So dV dt is minus 2, 9 pi over 64. The height at the given moment is 3, dH dt. This is the only quantity left to solve for, so I'm going to push everything else to the other side. Minus 2 times 64 would be negative 128. And 9 times 3 squared would be 81 pi. That goes underneath. All right, which is the same answer we had before, which is good, but it was maybe a little bit faster. So if you're the type of brain who needs to look at the equation and get all the bits, and then apparently I ran out of room on my hard drive, so here I am again. If you're the type of brain who likes to take the full equation, do the whole thing out, and then look at all the bits that you need, and then systematically go hunt for them, that's great. Do it the first way. If that was a bit scary to you, and you are looking more for shortcuts, and you think that you can go straight from the details of the model, that you can take that information and modify the model accordingly, and then take the derivative, then you will get there a bit faster. This takes a little bit more understanding about what you're doing and how to modify the model. I think the general theme here is that you're going to be handed some sort of equation. It will say the volume of a cylinder or something is in a pop can, and the pop can is inflating for some reason. And your brain has to know that a pop can is a cylinder. So you're going to write down pi r squared h. And then your brain should prompt you that the way the thing is set up, you're not going to have r and h independent of each other. There's going to be some relationship. So you go back and you dig through that text, and I bet somewhere it says a pop can whose height is twice the radius is expanding for some reason. So in there, there'll be some sort of clue that you're supposed to take h and replace it with 2r. And so if you do that in your original equation before you start doing all the derivatives, you might get something a little easier to manage. So good luck. It is a bit challenging. It will take you a bit of time to wrap your head around exactly what you're after, about which variables are static variables, like this thing here, when it said the height is 3, and which ones are dynamic variables, which are this one, right? How is the height changing? So it'll take you a minute to get your brain wrapped around that, but I promise you that if you put on a bike helmet, this is good advice, put on a bike helmet so that when you pound your head on the table for the first 48 minutes, you don't cause anything permanent in your brain. Eventually it will start to soften up so that the idea can sort of permeate in there. So again, good luck. If you need a hand, let me know. I guess that's it. So that's one related rates problem. It's classic, a cone. Hopefully it's got enough information there for you to figure the rest out. Okay? Good luck for the third time.